Shall we start? Hi, everybody. Long time no see, right? 2 weeks, right? So, sorry, what? Yeah, sure, some of you. So, yeah, we ended up with SVM last time, right? So we studied SVM. We got the idea how we can use SVM to classify something nonlinear, right? So it was a kind of tool that we could use to just learn some transform or some mapping, which is nonlinear. So this was the idea of SVM. And what we want to do today, we want to get into neural networks. And as I told you last time briefly, neural networks are, you can look at them as a kind of specific form of SVM. So it's a specific or class of support vector machines, which are very powerful. And it turns out that you don't really need, for most of the applications you have, to look for any kernel, because essentially you can build good kernels using neural networks. So we're going to get this idea here, this lecture, and just to recap a few things. So you do all remember linear classification, right? So what is a linear classifier? If we think of a two-dimensional world, then essentially a linear classifier is one line, right? So you have one line. On one side is one class, on the other side is another class, right? So if you think of higher dimensional space, then you're going to be a hyperplane. Again, one side of the hyperplane is one class, the other side is another class, right? So that is a linear classifier. We talked about it. We play around with it. And the only thing that we need to learn here is the weights of that linear model, right? It could also include some bias. Correct? OK, so that's it. And then we talked about the idea of support vector machines. So what was the idea? The idea was that when you have in your own space of data, you cannot linearly classify your data. Maybe you can take it to higher dimensions, right? Or maybe you can do some transform on your input, so you just extract a bunch of new features. And those new features can be classified linearly, right? So we had this idea that we had a bunch of points within two-dimensional space, and they were not linearly separable, but then we could just take them to the three-dimensional space. So those who are red are going higher in altitude. Those who are green are kept like lower in altitude, and then we can just find a plane which is classifying everything linearly, right? So that was the idea of SVM, but SVM does not specify your kernel, right? So it says just choose a kernel. It's your choice. You can either learn it, or maybe you do know it by heart, so you can put it, and then you do the linear classification on top of that. So that was the idea of SVM. And what we want to do, we want to get into the idea of neural networks. So some of you might have the deep learning course, and there we start with neural network. We'll look at them as a network of artificial neurons. So we're going to take an alternative approach here. So we want to just try SVM, but when we want to build our SVM, we use this repetitive form of linear transform with activation. And we're going to end up again with a neural network. Yeah? So that is the idea. So this is what we are going to do today. So we are going to talk about neural networks. We get the idea, what are they? And then once we understood them, we're going to talk about a few other things. For instance, we are just going to see how well we can represent everything with neural network. Essentially, we're going to see that any function, any binary function that we have, we can do realize it by a neural network. And pretty much we can realize any classifier or any function, we can approximate it by a neural network, which is why we call them universal approximators. And this is the main reason that we are nowadays always using deep neural networks. Okay? So if everything is clear, then let's get started with the first thing. So let's try to understand if just play with one simple binary problem. So what do I want to do? I want to learn what we call it the OR function. Okay? what is the OR of two binary variables? If I have two binary variables, x1 and x2, what is their OR? So if I have x1 or x2, what is it going to be? If they are both binary, when they're binary, they're either 0 or 1. So 0 or 0 is 0, right? So if x1 equals to x2 equal to 0, then this guy is 0, right? If x1 equals by 1, does it matter what is x2? 1 or 0 is, everybody? 1. 1 or 1 is 1, right? True or true is true. True or false is true, right? So it's going to be 1. Doesn't matter what is x2. Same thing about x2, right? So it's going to be 1 again, right? So if x1 or x2 is 1, then you're going to have 1. But if both of them are 0, then you're going to have 0, right? So now what I want to do, this is a binary function, right? Meaning that it's going to get one binary input, and then it's going to return me one binary output, right? 0 or 1 as the inputs, and the output is again 0 or 1, right? Now what I want to do, I want to see whether I can make a classifier which gets one of those linear models that we had, whether I can make any of them, which I give them this 0 or 1 inputs, and then at the output exactly I get OR of those 0 and 1s, okay? So the problem is clear for you, right? So this is the OR function. It is 1 if both of them, any of them is 1, and it's going to be 0 if both of them are 0. And then if I want to just solve the learning problem, I essentially can write it down in the form of, I can build one data set, right? So here is my data set. So what are the samples that I have? I mean, all possible samples are the 4 possible cases of the binary inputs, right? So the 2 binary inputs could be 0, 0, 0, 1, 1, 0, 1, 1. So I'm going to consider all possible cases. These are the samples, the data points that I have. And what are their label? The output of the OR value of these binaries, right? So I can write down the labels in this form, right? If I have 0, 0, then their OR going to be 0, but anything else going to get OR 1, right? Correct? So I can look at these guys as the samples. So those binary things as the input are the samples. And their output, I can look at them as labels. And what I want to do, I want to see whether I can make a classifier which can really realize this function for me, right? So the main question here is whether I can find one linear classifier, so I can find one weight and bias, which gets multiplied with x's, and then added up to that multiplication. And at the end of the day, when I just classify that particular output y, I'm going to get exactly 0 when OR value is 0, 1 when OR value is 1. Okay? So how can I solve it geometrically? Can I do it in two-dimensional space? Right. And this is a two-dimensional problem. So the input is two-dimensional, right? So I can sketch the data point inside the two-dimension, and then I can try find that line which is separating different labels, correct? So this is what we did before, so we are going to do the same. So here, as you can see, we have 3 different data points. So you see, second, third, and last data point, all of them are labeled by 1, right? So I'm going to show them with triangle. So there are 3 points that are labeled by 1, right? So 0, 1, 1, 0, 1, 1, all of them are labeled by 1. So we're going to show it like that. And then we have another point which is labeled by 0, correct? So this is another label, right? So that is the circle point, right? Now, can I find a line which is separating these two? Right? Everybody? Yes? I can do it, right? So I can just make one line like this, right? On one side, everything is labeled 1. On the other side, everything is labeled 0. So that's fine, right? I can solve this problem by a linear classifier, correct? So I can find that linear classifier, so that's fine. This means that I can just find 2 weights and 1 bias such that whenever I give a binary input to it, when OR value is 1, the output is positive. When OR value is 0, the output is negative. And this is fine for me, right? I just check the sign, everything is over. That works, but what about the XOR example? What if I want to do the same thing, but now instead of OR function, I am just dealing with XOR function? So let's look at XOR. So what is XOR? XOR is going to be 1 if the 2 values, 2 binary values, are different. But it's going to be 0 when they are both same. Okay? Meaning that if they are both 0 or 1, we're going to have 0. If they are both, one of them is 0, the other one is 1, then we're going to have 1. So this is going to be the data set, right? Again, we're going to have 4 different cases. For 0, 0, the label is, what is the label for the first data point? 0. The last data point for the remaining is 1, right? So you can just fill it out like this again, and then the question is whether we can find any linear classifier which is going to do the classification for us. So let's try to do this. Again, we'll look at it as the input. This is the label, and essentially we are just going to look for that linear classifier. So let's put the data points on the 2-dimensional space. So the points which are labeled as 1 are these points off diagonal, and the diagonal points are both labeled as 1, right? Sorry, 0, right? Now, looking at that, can I find any linear classifier? No, because the green points are on one line, the red points are on other line, right? You can never do that, right? So you can try this a lot. So you can just search for this line. But as long as, I mean, it doesn't matter how much you do it, you would never end up with a line which is separating both different labels, right? So what kind of problem is, how we can deal with this problem, given what we had before? We need to do, so if this is not linearly separable, what should we do? SVM, exactly, right? So we need to just find an embedding which is making everything linear, right? So first thing, I mean, you can be as obsessed as I am, and then you can try hard to show that this is not going to happen, okay? So it's not a very hard thing to do. So essentially, if you look at your linear classifier, you think that you have 2 different inputs. So you have x1, x2, and they are both binary things. And then you have 3 different weights, 2 real weights and 1 bias, being all combined with these inputs. And then at the end of the day, you want to look at the sign, right? So you can start with data points. For instance, you just put 0, 0 as the input. When you put 0, 0 as the input, then the output of the linear transform is going to be B. And for 0, 0, we want the label to be 0, meaning that we want this guy to be negative, right? So B should be negative. And then the next thing is that, for instance, I put 0, 1 as the input. And then the output of the linear transform is going to be W2 plus bias, right? And then for 0, 1, I want the label to be 1, meaning that I want this guy to be positive, correct? So W2 plus B should be positive. Same thing going to happen when I put 1, 0, right? W1 plus B should be positive. And if I set 1, 1 as the input, so if I have 1, 1 as the input, then I need sum of all of the weights, so the 2 weights and the bias, all of them, be negative because 1, 1 is also labeled as 0, right? So these are the all equations you need to get satisfied all together. If you just combine these 2 guys here, so the second and third one, so basically what you do, you just sum them up and then play around with the equation, you're going to end up with this fact. So you need the sum of weights to be more than minus 2 times B, minus 2 times your bias, right? And then if you get the last guy, then you just write it down again. You play around with the equation. You need the sum to be smaller than minus bias. Yeah? And now if I combine these two equations, I mean, sum of weights is the same here. Then you're going to conclude the sum of weights should be somewhere between minus 2 times b and minus b. Right? So can I have any number between minus b and minus 2b? If I want this to happen, what should be the sign of b? If I want any number, say number w, to be between minus b and minus 2b, what should be the sign of b? It should be positive, definitely, because I need minus 2b to be smaller than minus b, right? But you do know that b should be negative, right? From your first constraint. So that means that you don't have any solution, right? Meaning that it doesn't matter how hard you try, you would never ever find that line, right? So I'm pretty sure you see it on the diagram, but just in case you want to make sure, you can try like this, okay? So moral of the story, that line does not exist. The problem is not linearly separable. We need to go for SVM. So XOR function is not linearly separable. We do know how to deal with this kind of problem. That is SVM. And you might initially think that, okay, if we are doing SVM, so we need to embed it to take it to higher dimension, right? But the point is that you don't really need to do that. Why? Look at this guy, right? The issue is that, I mean, it doesn't matter how I put the line, there's going to be always at least one particular point with wrong label at one side, right? Now, if I want to fix this diagram that you see, if I get that top left triangle and put it somewhere below that line, do I get everything resolved? Look at this guy, the top left one, this guy here. This guy. If I take this one and put it anywhere below the line, then I'm going to have perfect classification, right? So I don't really need to go for a higher dimension. I just need to find a transform which gets that other triangle lower the line, right? Clear? So if I can make any sort of embedding of this form, which keeps the other points there, I mean, the green points are on the right place, but just that, troubling triangle is getting into its own region, then everything is going to be okay. Everybody's clear? Yeah? So this is the kind of embedding I'm looking for. And if I can find it, then essentially that embedding is going to extract me the features which I can linearly classify, and everything is over, right? So let's try to see whether we can find that phi x, which is a kind of, nonlinear embedding. So this is my suggestion. I just suggest this, okay? You're going to see shortly why I'm suggesting that. But what I'm doing, I am just writing it down in this form, right? So phi 1 is half maximum of the sum of x's and 0, meaning that if the sum of x's is positive, then I'm going to put that one. If they are negative, then I'm going to put 0. Same thing for the second line. Just I compute different, a linear combination, okay? So this is the embedding that I'm giving you as suggestion, okay? Now, let's try this embedding, see what's going to happen to the data points that we have. So the data points that we have, they are like, we have the green points, right? And we wanted the green points to be at the same place, right? So if I put 0, 0 into this embedding, what's going to happen? If I put 0, 0 into the embedding, what's going to be output of the embedding? It's going to be again 0, 0, right? Phi 1 is going to be half max of 0 plus 0 and 0. This guy is simply 0, so it's going to be 0. Phi 2 is going to be max of 0 plus 0 minus 1 and 0. So it's max of minus 1 and 0, which is again 0, right? So if I do that, then the point is going to be 0, 0. What if I just insert 1, 1? What's going to happen? If I put 1, 1, so here it's going to be 1, 1, right? Max of 2 and 0 is 2. Multiply by half, it's 1. Now, here is 2, okay? And then again, I put 1, 1 here. So it's going to be 1 plus 1 minus 1. So it's going to be 1. Max of 1 and 0, it's 1. So if I put 0, 0 or 1, 1, they are going to remain on their place, okay? But what if I put 0, 1 or 1, 0? What's going to happen then? If I put 0, 1, what's going to happen? If I put 0, 1, then phi 1 is, just put it in the equation. It's going to be half times max of, that summation is 1 and 0, so it's going to be half, right? So phi 1 is going to be half. What about phi 2? It's going to be 0, right? So phi 1 and phi 2 have 0. What if I put instead of 0, 1, I put 1, 0? What's going to happen? It can be the same thing because everything is a function of x1 plus x2. And in both cases, this is 1, right? So it's going to be, again, the same thing, correct? Everybody's clear? So if I give 0, 1 or 1, 0, I'm going to, any of those 2 points, I'm going to always end up at that point, right? Half 0. Now, for this problem, can I do it linearly? I mean, if I get phi 1, phi 2, can I classify them linearly? Yes? Okay. So sounds that the problem got solved, right? So I get this phi 1, and I do a binary classification on this phi 1, phi 2, and essentially I'm going to have my XOR function implemented. Everybody's clear? Any question on that? So this is essentially SVM, right? But I just gave you this particular embedding function, right? Okay. So now, maybe we can try to somehow write down things that we have done in this particular example in a more general form. Maybe we can have a bit of understanding what is happening here. So we have, say, d different inputs. We just thought of 2 inputs right now in the example, but in general, we could have d different inputs. We talked about it. Essentially, we just do some embedding. That embedding is something given. I just gave you that one. And that embedding is going to give us a bunch of outputs, right? A bunch of outputs. Those outputs could be essentially different dimension, right? So I could get 2-dimensional input in SVM, if you remember. We got like 2-dimensional input, then we computed a 3-dimensional output, right? So the feature space, those phis could be larger than the data space, right? M could be larger than D, correct? So you get your data, you just do the embedding on that, so you get potentially larger feature space, and then from that one, you basically do one linear classification, right? And the linear classification is always one weight. If it is, like our example, just a scalar output, we're going to have a weight vector and a bias. If we have more, say, higher dimensional problem, then we could essentially have a weight matrix and a vector of biases. Same thing, right? So at the end of the day, that linear transform, this is what we do by support vector classifier. And that embedding is going to give us the bunch of good linearly separable features, right? So these are weights and biases. So here everything is OK. On the right-hand side, we do know how to deal with that if it is a regression problem. We do know how to compute weight and bias if it is a classification problem. Again, we do know how we can do it, just logistic regression or whatever it is, depending on the type of problem. We are happy with anything on the right-hand side. The only thing that is looking like a black box right now for us is the embedding part. So essentially the question that we have is that how we can find the right embedding here. Okay? Like I gave you that for my example, but you might come up with this question like, okay, if it's a general problem, how can I come up with one solution, one embedding? So now, as I told you last time, so there are two different approaches to that. The first approach is the idea of doing engineering. And engineering is exactly what I did here, right? So I play around with the problem, I draw it on two-dimensional space, and then I saw that, okay, I need to just shift 1 point, lower the line, so I can do it because the problem is easy, and I came up with some suggestion, and that worked, right? So this is what we call it engineering, but you can simply understand that this is not really feasible in practice, because in practice you are going to have a huge dimensional input, right? And then even if you go for trial and error, that is not going to work, right? Huge cases, probably you don't shoot the right one, right? So this is not the cool idea. So this is indeed some sort of idea people initially were doing, but at some point, people got convinced that they need to do representation learning, right? So last time we talked about this idea of representation learning. What is the idea here? What was the idea of representation learning? What do we do here? Yes, we just go and learn the embedding itself, right? Meaning that, for instance, we think that the embedding is a kind of, function with a bunch of parameters. For example, it's a polynomial, and this polynomial is obviously, it could potentially take us into, nonlinear transform, and that this polynomial has a bunch of weights. So here, omega 0, omega 1, omega 2, these are the parameters. And we assume that we don't know them, right? So like the weight and bias in the linear model, we also keep them as kind of tunable parameters. And then we try to just find everything, the risk and the empirical risk in terms of that, and then we try to minimize it. So essentially, this is the idea of representation learning. We have a bunch of weights there. We have a bunch of parameters inside a kind of pre-assumed, predefined form of embedding. And then the thing that we are going to do, we are going to minimize the empirical risk while we take into account this fact that those weights in the embedding can be learned as well. So meaning that in the simple problem of linear classification or linear models, we usually compute we always compute the empirical risk R hat, and that empirical risk depends on the weights and biases, right? Because these are the only thing that we can design in the linear model, correct? But now, if I assume that I have a bunch of weights, then the empirical risk that I'm going to compute, that is going to be also depending on the weights or those parameters inside the embedding function. And if I can minimize that empirical risk with respect to every variable here, including those parameters, then potentially I can learn the right embedding alongside with the right weights and biases. Everybody's cool? Any questions? Okay, so that seems to be clear. Now, the question here is that you might ask me, okay, that sounds nice, but at the end of the day, you need to assume something. You need to have some model for your embedding, right? You need to assume something which has a bunch of parameters in it, and then we do all of things that we said in the previous slide on that one, right? What kind of key properties that embedding should have? Okay? This is one key question, right? Okay, you might say, okay, it totally depends on the form of embedding you assume. If you assume it is polynomial, it's going to be different from Gaussian, from anything else, right? You might say that, right? But the key point, the key point by neural network is that they say you don't really need to impose anything. The only thing that you need to have is one key property, which we're going to figure out right now. Okay? So let's think about this question a bit. Maybe we can start with the most simple kind of transform, and that is a linear transform, right? Meaning that I assume that when I'm computing the features for my support vector machine, I'm doing it again by a linear transform. What does that mean? That means that I have my x. So this x is d-dimensional, x1, x2, till xd. Now, I get one matrix omega. This is going to be, it could potentially be large. How many columns does it have? The number of columns should be d, right? Because it's going to get multiplied with this vector, right? So here is d. And if I want to compute m different features, how many features should I have? Sorry, how many rows should I have here? M, right? So it's going to be m here. And then I can potentially add it up with some bias. So I'm showing it again with omega, small omega. And what is the number of entries inside this omega? What is it? If I multiply this guy with this vector, it's going to be a vector of size m. What should be the size of this vector then? M again, right? Everybody's clear? So I get my x. This guy is x. Okay? I multiply it with a matrix, so I'm sending it to higher dimension, right? Say d is 2, m is 10. I'm getting my two-dimensional vector. I'm sending it to the 10-dimensional space, right? And then I can potentially add up some biases. And then this is the kind of phi I am computing, which is again m-dimensional, right? Everybody's clear? So this is the most basic kind of transform I can think, right? The most basic embedding is linear embedding. I mean, if you don't do even linear process on anything, then you essentially do nothing, right? Everybody's cool? Clear? So maybe we say that, okay, we can have a linear projection here. So I get x, I take it to a very, very high dimensional space by a linear transform. And once I have that, then I do linear classification. Okay? Let's see if this is going to work. Yeah? So now here, a few things. So maybe just to start getting some terminology. So this m here is something that I am going to fix for you, right? So for instance, I say I want to take this two-dimensional data point into 1,000 dimension, right? This is my choice. So m is my choice. This is a hyperparameter, correct? So this is a hyperparameter here. And this omega, and I mean both of them, the matrix omega and the vector omega, so both the linear transform and the bias, both of them are learnable, meaning that I assume that they are free parameters, and I want at the very, very end to optimize everything with respect to the weights of the linear classifier and these parameters. Okay? Everybody's cool? Questions? Now, if I want to do that, let me just write down everything. So I have my y. This y is the very output of the linear classifier, right? The final thing that I get out of the linear classifier, y. Okay? I have my y, and this y is the linear transform. It's linear transform times phi, which is the feature, plus the bias. You see it on the slide, right? Okay, now let me just replace that phi into this expression. What is phi? Phi, this vector here, this guy, is exactly this one. So phi is essentially omega times x plus a bias, right? Okay, so I'm going to replace it here. So I replace phi to be omega x plus omega plus b. And now, if I do a bit of multiplication and summation, I'm going to end up with this term, right? So w omega times x, this is one term. The second term going to be w times vector omega. And the last term is going to be bias, right? Everybody's cool? Nothing is specific, just linear transform, right? Correct? Question? No. Now, since I have done this, okay, now I do one modification. I'm going to call that W times omega, the first matrix, to be some other matrix, W tilde. Can I do that? They are both ways, right? I'm going to call it one matrix W tilde. I am going to call that last part, all of it, is going to be one vector. And that vector, I'm going to call it again vector B tilde, right? Now, how can I write down the output in terms of the input, not the feature that I extracted from the input itself? How can I write it down? I can write it down as one weight matrix times input plus a bias, correct? Did I do anything? Did my feature extraction do anything on my data? I'm not going to keep on till I get an answer. No, I didn't do anything. Everybody sees that? My output, look at it here. My output, if I don't do feature extraction, if I connect X directly to my linear transform, it's going to be one weight times my input plus bias. I ended up, again, same thing. And all of the parameters here are things that I can freely choose, right? Meaning that, at the end of the day, if I do perfect tuning of everything, then I'm going to end up, again, with the best linear model that I can think of, right? Moral of the story, this is not going to work, right? So linear transform is not the right transform which can extract the feature out of my input, right? Because if I do a linear transform, it doesn't matter how many times I do it. If I just get one point and just do 10 times of linear transform on that one, right? The very last output going to be, again, a linear transform form of the very first input, right? So it's essentially useless to do that. So our question was that what kind of property that transform, that embedding should have? And the answer is quite simple. You need to have something nonlinear. And the beauty of the neural networks is that it says it doesn't matter what kind of nonlinearity that is. Just put some nonlinearity and it's going to work at the end. Okay? So key point in the whole SVM world is that that embedding that you're computing, it doesn't matter what is its dimension. It doesn't matter how you compute it. It really needs to be somehow nonlinear. So if you do linear transform, even if you increase the dimension, it doesn't work. Yeah?
Sorry, why? I'm just confused on understanding. Why is it that when you do a linear transformation, it makes no impact?
If you think like geometrically, like if you have your points in one line, which you cannot do it, when you again take them to higher dimension, they're going to be again on the same subspace. So you can never do it, but if you think like, for this example of XOR, just try to take it to the third dimension by a linear transform. Everything going to always be on the same plane, I mean two-dimensional plane. Same surface. So you can never find a plane which is, again, separating them. So this is geometrically. Okay? Questions? So moral of the story, nonlinearity is the key point. And you might ask me, okay, was it the case when we did the XOR example? I mean, of course that was the case, right? It worked. So it means that we really did something nonlinear. So let's get back to our XOR example. Look at the XOR example. This was the kind of embedding I told you, right? Correct? So that maximum of something and 0. Yeah? So if I look at that guy, the whole, I mean, if you look at the thing that I show it with red. So maximum of some input and 0. This is a nonlinear transform. Right? So maximum of x and 0, it's going to look like this, right? So it's going to be 0 when x is negative. It's going to be a line when x is positive, right? This is nonlinear. But it's a very tiny bit of nonlinearity. But that is enough to help you solve the problem, okay? This is what we call it rectified linear unit. So ReLU function. This is the most basic nonlinear transform you can think of, okay? And what you have computed here, so the nonlinearity comes basically from that ReLU function here, right? Everybody's cool? So the feature we computed in the XOR example, it was indeed nonlinear. Okay? So that's going to be this. And now let's play around with the example a little bit. So I have that maximum of something in the first argument, or first entry, sorry. The second entry is again maximum of, or ReLU function of the same thing. So I'm going to take the whole ReLU function out of this vector. So I'm going to, instead of forming, this is the phi x, so ReLU function of the first term, ReLU function of the second term. So I'm going to write it down in this form. Okay? Fine? So ReLU function of a vector, it simply is operating ReLU on every single entry in the vector. Clear? Everybody's cool? Yeah? Okay, so this is our term, but the thing inside ReLU, what is that? What kind of transform is it on X? That is a linear transform on X, right? Correct? Because I can write that guy down. Look at that vector. So that vector, I can write it down as the one which I have inside ReLU. That guy is, so I have ReLU of half x1 plus half x2 and x1 plus x2 minus 1, right? This is my ReLU term, right? And how can I write it down? I can simply just write it down in a linear form. So I can just say that it's a linear transform of my x vector. I can just say that the first line, so it's going to be ReLU of x1, x2, some vector here. ReLU of this guy is going to be ReLU of this guy. And can you tell me what should I put here as the first term? Look at that guy. It's half x1 plus half x2. So it should be half, right? Correct? Half times this one plus, what should be here? 0. What about the second line? 1. So here is 1, here is 1. So I'm going to put 1 here, right? 1 times this one, x1 plus x2. What should I put here? Minus 1, right? Correct? So what is inside ReLU is a linear transform. That's fine. But ReLU is operating on that, making it nonlinear. So you can open it up exactly like what I did on the board, right? So that is essentially a ReLU transform, ReLU of some linear transform, and we can simply represent it in this form. So if I want to think about my transform from x1, x2 to the features that I extracted, before I get to the linear classification layer, so I essentially did one linear transform, but I did not immediately connect it to the linear classifier. I just did applied ReLU function on every entry I computed out of that linear transform, right? And then these are now my features that I extracted from data. Clear? Now, this guy is going to work, right? So if I connect this one into the linear classifier, we saw in the example that this guy is going to work, right? It's going to do perfect classification for us. So, moral of the story, you need nonlinearity, but that nonlinearity should not be something coming from Mars, right? So if it is as simple as ReLU, it could work. And this is the whole idea of neural networks. Okay, so moral of the story, if we want to just find this right mapping, right embedding, we need it to be nonlinear function, but that nonlinear function does not need to be very complicated. So at some point, people started to say that, okay, if we have a simple problem like ReLU, okay, essentially we get that, XOR, essentially we're going to compute one linear transform, then we just pass it through some nonlinear function, and out of that, we can just do linear classification, right? What if the problem is more complicated? What should we do? Okay, maybe we can just repeat it over and over, right? So maybe we can add another layer of that, right? So just compute a linear transform, pass it through some nonlinear function. Now I have a bunch of features which are nonlinearly depending on the input. But again, the problem is complex, so I again do the same thing on these features. Again, I transform them linearly, and I do some nonlinear operation, and I keep on going, right? So as problem gets more complicated, I can keep on doing this more and more. And I might hope that at some point, what I compute at the very last layer is going to be something that is linearly separable, and I can simply pass it through my linear classifier to classify it perfectly. Everybody's clear? Any questions? No question? Cool. So this is what we call it feed-forward neural network. And we are going to unbox it today. Okay? So we're going to open it up. And you might say, okay, why this is neural network? So we're going to also show that as well, which you can think of everything happening here as a network of single neurons operating on different parameters. So, yeah. Yeah, of course, definitely, yes. This is the idea of perceptron, of course. You can definitely do that, but this is not a cool thing. Like you're going to see later that you really need, I mean, you needed still something with gradient, right? Yeah. But that can essentially work, okay? Sorry? Yeah, of course, definitely, yeah. Questions? Okay, so if you got no question, then let's start with the feed-forward neural network a bit. Then we're going to have a break. So feed-forward neural network, so if we think of a feed-forward neural network with L different layers, actually here is L plus 1 layers, but this is L different hidden layers. So this is one feed-forward neural network with L different layers between your input and output layer, okay? So if you look at this guy here, let's just clean it up a bit. So if, for instance, I thought I have immediately the other slide, but no, I'm just now introducing the artificial neural networks. Artificial neurons, okay. So if we look at this network, we can essentially show it as individual parameters, or network of individual components, which people used to call them artificial neurons. And a bit of history behind that, like SVM, as I told you, was somehow developed later on, okay? And people who did SVM were not really thinking in the world of neural networks. So neural network was something else. People were trying to understand how neurons work, how our brain functions, and then they developed some other computational models. SVM was the VC theory, which was developed quite later. And then at some point of time, people started to see that you can get those neurons and put them as the parameters here, which make your embedding function, or learnable embedding function, to be represented, okay? So what is an artificial neuron? So artificial neuron is a kind of computational model, is the most basic computational unit that you could think of. And that is essentially a combination of a linear transform, a linear computation, and a nonlinear transform. So you can think of it as having multiple inputs. So x1 to xt, your data, is the input to this unit. And these units are going to just first compute a linear transform, right? So that A here, you can simply think of it as the linear model out of those x's, right? So A is the summation of all of those weights being multiplied to the corresponding x's plus the bias, right? That is A. And the next thing that it's going to do some nonlinear transform on that linearly computed parameter, okay? So once you computed A, which is a linear transform of your x, then you are at the very end of day, do one nonlinear transform. That nonlinear transform, what do we call it? Any idea? Activation function, right? So that is the activation function. So this is what we call it, activation. And the reason we call it activation is because we think of biological neurons, right? So people model it like that. So if you touch something, then like your body starts to feel that, is because there are some signals passing through the synapses inside your neurons. And at some point, when these signals are going to pass a threshold, then they kind of fire. And then at some point, you start to have the feeling, right? The stronger the signal is, the harder you're going to feel that thing, right? So this is why it's somehow activating the neuron, right? It just make it to just give you to fire at the output. So that activation function could be a very, very simple thing. As I told you, it could be a ReLU. You can also think about more complicated things. So theoretically, if you put any nonlinear function, it should work. Yeah? So it could be a ReLU function. It could be a step function. We don't like this guy because when it comes to training, it's going to make us trouble. You're going to see it next session. It doesn't have gradient. This is the issue with that one. But essentially, theoretically, if you put that one as your activation function, still there exists a bunch of ways which are going to classify your data properly, but probably you are not able to find it efficiently. You can use sigmoid. It's another function. We already discussed it before. So this was the thing which we used to compute the probability at the output of the linear transform in logistic regression. We can use that one that is still nonlinear, and it's a very smooth function, so we can use it. You can think about tanh function is again smooth and nonlinear. You can think of soft ReLU function. So essentially, this is the smooth version of ReLU function, because you look at that expression here. If I keep x to be very large, then this is going to be a log of 1 plus e to power something large, right? And then I can drop that 1. Approximately that is e to power that x, right? And log of the exponential function is the exponent itself, right? So when x is very large, that is linear, correct? And when x is very small, then 1 plus e to power that thing is pretty much 1. So that e to power very small number or very negative number is roughly 0. And then you would say that, log of 1 is 0. So essentially, it's going to start from 0, and then it's going to somehow get to touch the y equal by x line on the other side, but it does it smoothly, right? It doesn't do it with edge. So this is another version of ReLU function. But any of these functions, you can put it as the activation function. And if you use any of them, then essentially, at least the example we solved today, going to work perfectly. So there's no problem with that. Okay? Cool. So now I want to just unbox that fit-forward neural network that I showed you a couple of slides before. And for that one, I'm going to use a shorthand notation. So this is the shorthand notation. So I'm going to show this whole artificial neuron as one circle. And that circle, this middle projector is showing it better. So that guy is yellow, so it's different in color. But when I write down h inside it, I simply mean that h is computed after activation. Okay? So this notation simply means that there are some inner processing here. So inside that h, I first compute the linear transform. And after computing the linear transform, I activate it by some activation function. And the output of that activation, nonlinear activation function, is going to be h, right? So h is essentially the output of your ReLU, for instance, right? Okay, and here, those edges, all of those links that you see in green are the weights and biases which essentially you can learn. Meaning that when you are trying at the very end of the day to minimize the empirical risk, they are parameters which you can essentially play with, right? So they are learnable, you can play with them. Cool. So these are learnable. The output at the very output of that neuron is actually the output after activation. And as I told you, why we call them neuron, because they are the basic computational model for how or a logical neuron work. Okay? Now, do you want a break or should I keep? Yes? Okay. So 5 minutes. I mean, today I think I am fast enough. So we can have 7 minutes, okay? And then we can go on. Yeah, I think you wrote me, right?
Yeah.
I think you were the one, okay.
I tried, so you're saying to rewrite it like this.
Yes, exactly.
So then, does that also go inside of this, or is it still this whole dog?
No, this is the yes, exactly.
This is still our,
Yes, and then X. Oh, you're writing the supplementary assignments. That comes
and then when I try and like plug your computer, I'm this crazy. Which can't happen, but would mean that both of them are zero.
Can you try?
no, both of them are zero.
Yeah, right. Well, they can be positive, they all have to be positive.
They should be zero
So I sub that into
When you do it, like if you add this V and then the weights, something like that, then essentially you don't need that. Right, that's the question. I'm trying to give you the hint how you can drive it without doing the straight. If you try to I mean, if you do that equation, you're going to end up with the same equation. So one of the equations you get out of the component slide is that you have to
so I shouldn't do
both of them. I mean, if you do both of them, then you have to see one equation. So flat.
yeah. That's why I don't do the first one. I know.
Yeah, okay.
But still, I can't.
Really get the right one. Okay, I can try it once. I mean, I tried it once before I just put the sign. At that point, the grammar was right, but I will double check.
I mean, it should, like, maybe hot. Literally 7.
Yes, exactly. Yeah, let me double check it. So maybe I have a mistake. Like maybe in the slide I have one extra position. Yes, exactly.
Are you not be posting like a list of topics?
No, because this one is a bit more basic, right? So you can come up with
The loss function.
physics.
The loss function. Obviously it's physical. It's better to find the loss function.
Well,
That's just in my brain.
yeah, I need to see your proposal.
Okay, we will. I think the loss function comes after like we have to find like our project topic first, and then the loss function comes after that.
Yeah, but this is some problems like sort of self-supervised problem. Sometimes out of the physics of the problem, you do know what is the right thing that you want to minimize, but you don't know the process, so you try to learn that, and then you find out from it's lost function. You can think of basic optimization problem. The objective is to remove loss.
That's all our questions.
Yeah.
Thank you.
So, shall we go on? Okay, so now let's see if we can write down this architecture in form of or in terms of those artificial neurons. Okay, how can we do it? Let's look at the first layer. So what do we do in the first layer? In the first layer, we do a linear transform, so we get that omega 1 times x plus some bias. So this is the first transform. And we get from d-dimensional to an arbitrary number of outputs, right? So let me show that first layer, the number of number of outputs in that first linear transform. Let me call it M1, and I put that 1 on top of M so that you don't get confused. I hope that it's not more confusing, but M1, I simply mean the length of the first layer. So here you're computing, you're getting x as the input. So this is your x, this guy is d-dimensional, and then you have this linear transform. So this is omega 1 x plus the bias, and then at the output, I assume that I have m1 different outputs, right? So these are different values, so I can show them with, say, A1, A2, and so on till M1, right? So I can show it that way. So this is going to be the output vector of the first linear transform, A1 to AM1. And then the next thing that I can do, I can just write it down in terms of everything that I do have. So I'm going to write it down in terms of the input. So there's one matrix omega 1 getting multiplied with my vector x and then added up with some bias. I can open up that matrix and the bias vector as well, and it's going to look like this, right? Correct? Okay. So here, when you look inside this matrix, so I put 1 to D as the argument for columns, and then for rows, I do have the index, okay? Now, don't get too much confused with that. Let me just write down A1. This is for layer 1, 1, okay, the first entry. So this is the first layer. So now I'm talking about this guy, okay? I want to write that guy down. And can you, based on that matrix vector product, can you tell me what is that first output? What is the first entry in the green vector? How can I write it down? So it's going to be the first row of my matrix, correct? First row of my matrix multiplied with x, correct? So I am going to have omega 1, so the 1 is here, first guy, multiplied by x1, right? Then it's going to be the next one, so it's going to be omega 1, 1. This is the second guy, multiply with x2, and you keep on going like this till you have omega 1, 1, the last entry in the first row, times x d. Correct? Right? Now, anything else I need to add to that? The bias term, so it's going to be omega 1, 1. So this is going to be omega 1, 1, right? So I can write this A11 simply as the summation of omega 1, 1 I times xi plus omega 1, 1 here. And this I starts from 1 and ends at d, right? So a linear combination of my x's plus some bias, right? Now, if I just, instead of the first entry, I think of entry j, what's going to change in this summation? The index is going to be j, right? So this is going to be j, this is going to be j, this guy is j, and this guy is j as well, meaning that I'm going to have j here as well, right? So this is, aj1. So the jth entry at the output of that linear transform, matrix product, I can write it down as the linear transform of my input plus some bias, right? Correct? Okay. Now, what's going to happen next after I compute this A? What do I do to that value, that linear computation? I pass it through the activation function, right? So the corresponding guy after activation, that is essentially the output of one artificial neuron, right? And what are the weights of that neuron? What are they? Come on. Yeah, go on. These omegas, right? These omegas are the weights. Do I have any bias? This guy is the bias, right? So this thing here is a linear transform. It's exactly the same thing that I compute in a neuron. And then at the very output, I just do the activation. So what I can think that essentially every single entry after activation is output of one neuron. So I can say that the first guy after activation is just output of a neuron. So I can just remove that guy and put one neuron here. The second neuron is computing the second output, and so on till the last one, right? So essentially, that linear transform getting now rectified or being done any nonlinear activation on that, I can simply look at it as a kind of, a bunch of neurons, every single of them just being activated with the same function, right? Everybody's cool? Right? And the weights and the biases of those neurons are somehow written in that weight matrix omega and the bias. Correct? Great. So if we think like that, so we can repeat this, replacement layer by layer. And at the very end of the day, we're going to have L different layers. Every single of them has a bunch of neurons, and those neurons are activated with a bunch of weights and biases. Are weighted with some weights and biases and are activated with some activation function, right? So what you are essentially doing, you are getting your input, you're passing them through some artificial neurons, you compute a bunch of outputs, right? And then again, you get those features, those output features, and you do the same process on them. And you keep on doing it for L different times till you end up with something that you think is a right feature that you can do linear classification on that. Clear? Questions? Okay, great. So if you got no question, then this is going to be the output. So the outputs of the last layer of the neurons is going to be the final features that we are extracting. So this whole neurons are going to represent our embedding function. And then we have those features, we just do linear classification on top of that. Okay? Now, depending on the problem that you have, it could be a regression problem, it could be a classification problem, you really don't care, right? At the end of the day, you have your features, and you can do either linear regression on them, like in this example. So if I want to have a linear, so a real valued output, I can simply just do some linear transform on those features phi. And essentially here I have a bunch of, this is exactly the same thing we did on the board. So I have again a bunch of linear transforms, and every single of them is computing one output. If I have a classification problem, I can look at those features as the kind of features that are representing my data, and I try to just linearly classify it, right? So for instance, if we have a binary classification problem, then essentially at the very end of the day, when I have different features, phi1 till phi m, I'm going to get them and do linear classification on those phi values, right? Meaning that I multiply every single of them with some weight, add up a bias, I compute something like y. Y is no real scalar, and then I look at the sign of that guy, right? If that guy is positive, I'm going to label it as, y1. If it is negative, I'm going to label it as 0. So essentially, what I do have as the new network of those neurons, that can do embedding for me for any problem, right? If I have regression, if I have classification, it doesn't matter. I just repeat this repetitive architecture or repetitive collection of neurons. I do it as much as I need, and finally I get something at the very output, which are a kind of pure features, which can be linearly transformed into what I want, right? So that is the idea of representing or embedding function by a network of neurons. And given that, now we have essentially what we had was the neural network, and we can define a bunch of things. So first of all, it's now obvious for you why we call it neural network, right? Because every single of those linear transform and then being nonlinearly activated, every single of them, you can think of that as a layer of neurons, right? And then you are making a network of lots of neurons, so it's a neural network, obviously. So this is the first thing. The second thing is that in this neural network, we have 3 different types of, say, components. The first component is the one which is fed to this whole embedding, right? Remember, anything between x and y, before getting to y, anything between these two is somehow your embedding function, right? So you start with x, you compute all of those embeddings, you get phi values, right? So anything in between, you can think of it as a function. So neural network is a super complicated function at the end of the day, right? So these x's which are fed to that function, which are fed to that embedding, are the input layer in this neural network, okay? Then, once you have done everything, that at the very, very end, you are going to compute a bunch of linear computations on the features you extract by that, embedding function, right? That is what we call it the output layer, okay? And anything in between, those layers of neurons, we are going to call them hidden layer because they are somehow hidden to us, right? They are within the embedding function. And I mean, it's true that we opened it up here, but we can think of it as a kind of black box, right? So that is a hidden layer. Clear? So how many hidden layers do I have here? L different hidden layers. Great. So that is the terminology on neural networks. And when you have a feed-forward neural network, then essentially you can think of every single layer to be, the output of every single layer to be a vector of hidden features, right? So you have X, you pass it through the first layer, so you can think of the whole layer to be one, vectorized form of function. And then you have X, you compute H1. That H1 is a vector of hidden features. And again, you repeat the same operation on H1, you get H2. Again, another bunch of hidden features. And you keep on doing it till you get HL. HL is essentially computing the embedding that you want, right? So now, if you look at it this way, then we can define a bunch of few things. The first thing we can define for it is the depth of a neural network. So what is the depth of a neural network? It's actually the number of hops that you should take in order to get from input to the very output, right? So this is actually the number of layers that you have. You exclude the input, but you include the output, right? So this is the depth, right? You start from input, and you're going to take that depth to get to the very output. Now, here in this diagram, what is the depth? What is it? Everybody? Somebody from back of the lecture hall? Can you tell me what is the depth here? Just to make sure everybody got it right. Is it L or L plus 1? You should exclude input layer, so I don't think of X, but I include the output layer. So how many hidden layers do I have? L, and I have one output layer, it's going to be L plus 1, right? So this is L plus 1 here. So the depth is L plus 1. Now, one thing I'm going to tell you later on, but do you have any idea what is a deep neural network? A neural network whose depth is very large. What should be the depth? It should be more than 2. Okay? So it means that you have more than one hidden layer. That's a deep neural network. And you might wonder why? Because, we're going to see it today, okay? People initially thought, okay, one hidden layer is enough, so a shallow neural network is enough. But then it turns out when you make it deep, then it's going to work better. Okay? So that is a deep neural network, but for the moment, the depth is here L plus 1, the width of one layer. The width of one layer is the number of neurons you have in one layer. Okay? So basically, you just count the number of outputs you get at every layer. That is the width of one layer. So this is usually defined for one layer. So those mj, m superscript j, these are the width of the hidden layer in our previous slide. And there is no specific definition of the width of the network, because width is for one specific layer. But some people call the largest width all across the network to be the width of the network, okay? So if you find the hidden layer, or any layer, including the output layer, which is the largest width, some people call that one the width of the network itself, okay? Now, I told you that what we had here is a feed-forward neural network. And why do I call it feed-forward? Because when I want to compute the output, I have to give the input, and I always go forward, right? I never get any cycle in my network, right? You might wonder, can I have a cycle? Sure, you can have it. And that's going to be recursive neural network, right? So we're not going to cover it in this lecture, but you can essentially have it. Yes?
So on the previous slide,
Yeah.
when you say in general the width changes from one layer to another,
Yeah.
is the width just always referring to whatever layer you're at
Yes.
until the very end?
Whatever layer you're in. So the width of the first layer is M1, second layer is M2, and so on. Yeah? But if you hear somewhere people say width of the network, then they usually mean the largest width.
Okay. So like, for example, if you were at layer 2 right now,
Yeah.
the entire width would be L plus 1 minus 2, right?
Sorry?
Oh, wait, no.
Sorry, I didn't get your question. No.
So if you were at layer number 2,
Okay.
would the width of the network relative to layer number 2 be equal to L?
No, width is for the layer. It's just how many neurons you have in that layer. Yeah. So no, don't get confused with depth. I'm not talking about depth.
Oh, wait. Okay.
Yeah. Okay. So like, say for instance here, in this one, maybe that one is the easiest one is here. Right. The first layer I told you have A1. I mean, just forget about the superscript. A1 till AM1, right? Then the width of the first hidden layer is M1. Okay? You got it? Yeah. Okay. So, yeah, that is the width. And yeah, any questions? So now, feed-forward neural network, you always go forward, right? You don't have any cycle in your neural network, correct? So meaning that you're not going to compute some hidden feature in the middle and then again feed it back to some other layer as input, right? Can we do it? We can do it. If you have heard of LSTM, for instance, that does it, right? But we are not covering it in this lecture right now, okay? We don't cover it in this course. Yeah? But this is feed-forward neural network, meaning that everything fed to it, it's going to compute the next layer till you get to the very output. Now, I also told you this is a fully connected architecture or fully connected neural network. Why I do call it fully connected? Because when I just showed you the diagram, every single neuron in any layer is connected to anything in the previous layer, right? So the first output, this guy, when I'm computing it, this is the output of the first layer, right? So when I'm computing any neuron, output of any neuron in the first layer, it is connected to all possible x's, right? Correct? So you have all of those, previous outputs to be the input of your every single neuron in the layer. This is fully connected. Can we have non-fully connected? Yes, we can. And that is the convolutional neural networks, which we are going to shortly discuss towards the end. Okay? So you could have them. So not necessarily you need all of them being connected. But here we are thinking of the most complex form, which is fully connected. Okay? Now, these fully connected are the thing that many people call them multi-layer perceptron. And why they call it multi-layer perceptron? Because if you remember that linear classifier that we had, when you just do the classification using the step function, the sign of the output, it was somehow called perceptron very long time before by Rosenblatt. And then people thought, okay, essentially every artificial neuron is somehow a perceptron which is just activated with something non-step function, not sign, right? But it's still activated with some activation function. And we are putting them in form of layer, and then we have multiple layers. Then this is a multi-layer perceptron, okay? Well, if you want to be very strict, this is a misnomer. This is why if you, for example, check Wikipedia, then it just starts that MLP is multi-layer perceptron is the misnomer of the fully connected feed-forward neural networks. But now it is a very conventional misnomer. Like everybody says MLP, it's going to make total sense, okay? So, now, let's just get back to our XOR problem. Let's try to just check these definitions that we played around with. Just look at them in this example to see whether we understood everything properly. So, here, as you can see, I have two different inputs. So these parameters that you see here are exactly the parameters we had in our example. So if you remember, we had 1/2, 1/2, and then, 1/2, 1/2 added up, 0 bias, then activated by ReLU, right? So I exactly put everything as before, okay? Now, You look at this guy. Now, first of all, what is the input layer? The first guy, right? X1, X2. So these are the input layer. And what is happening inside every single of those hidden neurons? So for instance, in H1, or it doesn't matter, H1 or H2, you always have whatever coming from the previous layer, multiply with their weights, added up, added with a bias, and then activated by a ReLU function, right? Correct? So this is what is happening inside those artificial neurons, right? And what is happening inside that output neuron, that guy? So whatever you get out of those hidden neurons, so H1, H2, whatever the output is, they are going to get again multiply with their weights, added up with this bias, and then you have a value y, and you can essentially check the sign of that y, right? If y is positive, you're going to say 1. If y is negative, you're going to say 0. Correct? It's again a neuron, right? Everybody's clear? So, now, input layer, X1, X2. We have one hidden layer. We have one output layer. What is the depth of this neural network? What is it? 2? Yeah? And what is the width of the hidden layer? It's again 2, right? What is the width of the output layer? 1. What is the width of input layer? 2. Great. So you got the idea. So the depth is 2, and the width of the first two layers, input and hidden, is 2. The depth of the last layer is 1. One question, is it a deep neural network? No, it just has one hidden layer, right? If I add one other hidden layer, then it's going to be deep, okay? Now, right, so the width here is 2, the width here is 1, and that's it. Now, let's try to just check what is happening inside this guy. So, one other thing about the being fully connected. Is it a fully connected neural network or not? H1 is connected to anything before it, right? So X1 and X2, both of them are connected to H1, right? H2 is also connected to anything in the previous layer. H2 is also connected to X1 and X2, right? What about the output layer? If you look at the output layer, also the output layer is connected to both H1 and H2, right? Anything in the previous layer. So it is a fully connected neural network. Okay? Clear? Now, so the first layer is fully connected, the second layer is fully connected, so this is totally a fully connected feed-forward neural network, or what we call it MLP as well. And now let's just see what is happening inside this neural network, the whole computation process that is going on in this guy. So say I am giving 0, 0 as the input, right? Just remember, we are just realizing the XOR function, correct? So what is the XOR of 0 and 0? It's 0, right? 0 XOR by 0 should be 0. They are the same, right? Now, I am giving 0, 0 as the input, and what is going to happen? That first 0 on top is going to get multiplied with its weight. What is its weight? Please? It's half. Great. The second 0 down is again going to get multiplied with its weight. What is its weight? Half again, right? So half times 0 plus half times 0 going to be 0. What is the bias of the first neuron? It's again 0, so 0 plus 0 is 0. So what comes out of the linear transform is going to be 0, and the ReLU function is going to give me 0 at the output, right? So the first hidden neuron is going to give me a 0. What about the next guy? Let's look at the next guy. If I pass 0, 0, what is the weight of the corresponding to X1? What is the weight? That is? Everybody? 1, right? What is the weight corresponding to X2? It's again 1, right? So 0 times 1 plus 0 times 1 going to be 0. What is the bias? Minus 1, right? So 0 minus 1 is going to be minus 1, right? So minus 1 is coming out of the linear computation. This is what you see at the input of ReLU function, right? And then when you pass minus 1 over ReLU, what's going to happen? 0, right? So you see, there is nonlinearity here happening, right? So minus 1 is not linearly transformed. It's just nonlinearly transformed, right? To 0. It's impossible that you can do it with linear, right? So it's impossible. You have everything like on the right side of ReLU. One of them at least should be on the left side of ReLU. And this is what is happening here. So now you have 0. So both hidden neurons are giving us 0. Now when I pass those 0, 0 through the second layer, so the first 0 gets multiplied with 1, the lower 0 gets multiplied with minus 1, which ends up being 0, minus the, plus the bias, which is minus 1/4. So it's going to be minus 1/4. And then if you look at this minus 1/4, you are going to classify it as 0 because it's a negative value, right? So 0 is going to be the output. This is exactly the XOR that we want. Everybody's cool? Clear? So you got the idea? What is a neural network? How it functions? Right? And the whole key point is that we need to have that nonlinearity. If you don't have it, it's not going to work. Right? Great. So if you got no question, then I'm going to bore you with a bit of discussion, which just give you this idea why these neural networks are very important or very powerful. So this is the whole idea of expressive power of a neural network. What I want to show you here, I'm going to just discuss it briefly, but through that discussion, you're going to get the idea. Pretty much any function that you think of, you can somehow approximate it by a neural network. Yeah? And you also get the idea why we need to have a deep neural network. Because essentially, you see, as you increase the depth, you're going to need less neurons to represent that function. Okay? So let's get to that one. So the question that we try to answer here is that how expressive a neural network is. And what do I mean by expressive? It means that, say, how many functions I can represent with one given neural network. Okay? So I give you one neural network. What is the space of functions I can represent with that neural network, right? So when I talk about the space of functions, it could be a bit hard to think of that because, well, if we think of a kind of a linear input, then the space of function is essentially infinite, right? Infinite number of functions you could have. So maybe we can first get stuck with binary functions, okay? What do I mean by a binary function? I simply mean that I have binary input and I have binary output, okay? So if I think of a binary function, that function gets the different binary values, x1 to xd, as you see there. And then the output is going to be a binary number as well. So it's going to be again 0 or 1. Now, this binary function, I can always show it with a truth table, right? Because, I mean, they're finite. I mean, it could be very large depending on the value of t, but at the end of the day, it's going to be a finite number of cases or combination that I can inject to this function, correct? So if I think of d-dimensional case, I can start with every input being 0, then all of them 0, the last one is 1, then all of them 0, 1, 0, and then 0, 0, 0, 0, 1, 1, and so on till I just cover all possible cases, correct? Right? So, and for each of them, I could either have 0 or 1 as the output. Now, one question. Can you tell me how many of these functions I have if I have d different inputs? Let's think of one function, okay? If I have one function, like this one I'm showing here, how many combination cases do I have? How many rows do you see in this truth table? Yeah, you did it right, just tell me. I'm pretty sure everybody got it right, just tell me. How many rows do I have here? 2 to power d, right? So this truth table is going to have 2 to power d different rows, right? So this is the first case, which is 0, 0, everything 0, 0. The next one is going to be 0, 0, 1, and so on, right? And then if you count this number, how many of them do I have? 2 to power d, right? Correct? Now, this is the number of possible combination for one function, right? For one function. Now, your function has all of those red values, and every single of those red values could be either 0 or 1, right? Now, how many functions do I have? So this function, this is the output function, f of x. This could have different inputs, and the number of possible inputs this function could get is 1 to 2 to power d, right? And every single of them could be either 0 or 1. Now, how many functions do I have? Please? Yeah, just go ahead. Sorry? 2 to power? yd plus 1? No. I think 2 to power 2, yes, exactly. 2 to power 2 to power d, right? So you have 2 to power d different cases. Every single of them could be binary, right? So you are going to have 2 to power 2 to power d different cases, okay? So this is the number of possible binary functions you could have if you have d different inputs. So every single truth table gonna have 2 to power d different rows, and you have how many of those binary tables? 2 to power the number of cases, right? 2 to power 2 to power d. And just to see it exactly on like two-dimensional case, like when d equals by 2, then essentially your table is going to have 2 to power 2, meaning that it has 4 different rows, right? 0, 0, 0, 1, 1, 0, 1, 1, right? And then at the output, the last column of this table, you could either put all of them 0, you could make them 1, 0, 0, 0, 0, 1, 0, 0, 1, 1, 0, 0, and so on, right? So you have 4 different cases, then you're going to have 2 to power 4, which means 16 different possible tables, right? So this is the total number of functions that you could have in this case. Everybody's clear? Right? So I have this much of functions. This is good because I want to check how many of them I can represent by a neural network. If I do know what is exactly the dimensions, what the parameters of this neural network. Okay? Any question? Okay, now, one thing. If I have in this binary function, if I have just one of the possible values of the function 1, if I just have one of them 1, can I realize that by a linear classifier? I can always do it, right? So it's exactly the problem we started with, right? So one of them is going to be, for instance, circle. Everybody else is going to be triangle. You can always plot one hyperplane, which is separating that circle from triangles, right? It's also the case if you have only one of them 0, rest of them 1, right? So you're going to have one triangle, everybody else circle. Again, you have a hyperplane, which is separating them, right? So meaning that if you have one single 1 or 0 at the output of your function, then essentially you can realize it by a linear classifier, right? And a linear classifier is an artificial neuron, correct? Everybody agrees? Silence? So what is a linear classifier? It's going to compute the linear computation, right? It's going to get the linear transform of whatever the input is, and at the output, it's going to check at the sign, right? So your linear classifier is always computing. Your linear classifier is going to compute. This is your linear classifier, and your linear classifier is going to compute the linear transform x1, say, till xd. linear transform of them, maybe some bias here as well. So W1 till WD. This is the output. And then after doing that, it's going to check the sign, right? Correct? Right? And then the output is going to be either 0 or 1, correct? This is the linear transform. This is the activation. So this linear classifier is nothing but a neuron, right? Artificial neuron whose activation function is simply the step function, right? So I can realize that those kind of functions simply by a linear classifier, right? And this means that I can realize those functions by a single neuron, right? So if I have just one neuron, I can realize such functions, right? But you might say not all of them are the same, right? Not all of them are in this form that they have only one single 1 or 0 at the output, right? But it's no problem. I mean, if they are not the same, we can do exactly the thing we did in XOR, but in a more efficient way. Maybe we can decompose them in forms of functions which have only 1, 0, or 1 at the output. So what do I mean? So if I have any function, any binary function, I am going to write it down at the end of in terms of a truth table, right? And I can just look at those parameters which are 1 at the output of that truth table, right? And then I sum it up in form of those subfunctions. So what do I mean? Look at this function f10. This is the 10th function if you follow what I did in the previous slides, right? And this function does not have single 1 or 0, right? It has 2 1s and 2 0s, correct? But can I write it down in form of these two functions being added up? Is it correct or wrong? Everybody agrees? Yes? I do know it's a bit late and you're tired, but a bit of interaction would be appreciated. So you got it, right? What I'm doing here, right? So when I have more than a single 1 or 0, I can decompose it in terms of those kind of functions which have only single 1, right? And can I realize f2, for instance, with a neuron? Yes, I can do it. Can I realize f9 with a neuron? I can again do it, right? And now, if I have the output of those neurons, maybe I add them up, right? And this is going to be the function that I want. So essentially, I get my x's in the example, for instance, that we have. I pass them through 2 neurons. One of them is realizing f2. One other is realizing f9. And if I add them up, so every single of them is one linear classifier, right? One single neuron with the activation function being a step function. And then when I combine them together, I am going to get my f10, right? Correct? Yes? Okay. What is it on the board, on the slide? What is this architecture? It's XOR, exactly. But what do we call this kind of architecture? That is a neural network, right? This is a neural network, right? 3 different neurons, like F2, F9. I mean, that output neuron is just simply one summation, but still you can show it as a neuron, right? Everybody's clear? So F2 and F9, they were linearly separable. I could represent them with a single neuron. There are a bunch of functions which are not linearly separable, like this F10. And essentially, I can just realize it with a bunch of neurons, right? Every single of them is just representing one of those terms in the decomposition, right? Now the question here is that if I have d different inputs, so can I do this thing that I showed you in the previous slide? So can I realize it again with one single hidden layer, as I have done here? So here are the hidden layer. I just have one hidden layer. Can I, if I have a d-dimensional input, can I do it with one single hidden layer? Of course I can do it. Again, I am going to decompose it into those terms. And then every single of those functions, I can realize it with one neuron. I just put them in the hidden layer. And then when I add them up, I'm going to get my function at the output, right? So I can essentially realize any of those functions with one hidden layer. But the question is how wide that hidden layer should get. Huh? If I have d different inputs, how wide the hidden layer should be. If you want to answer that question, I'm going to give you a bit of like cheating here. So it's known that the worst case scenario, you might take later this day or later even this week, you might think about this. Probably those of you who had logic circuits and you played around with the Carnot table, you already Carnot map, you know this particular argument. But the worst kind of function you can think of is the one which is just changing 0, 1 every single row, right? So the first row, for instance, is 1, 0, 1, 0, 1, 0, so on, right? So half of the possible cases are 1, half of the possible cases are 0. This is the most complicated form of the function, binary function you can think of, okay? Just take it from my side, okay? So if this is the most complicated case, what should I do? So for instance here, this is one of those, very complicated ones. This is essentially XOR. XOR is known in its own two-dimensional space to be the most complicated binary function. But here, as you can see, you have 4 different cases at the output of the function. Half of them are 1, half of them are 0, right? So this is the most complicated form you could have. And if you have a form like this, now how many neurons do you need in the hidden layer? I want to write it down in this form, right? I want to write my function f in the form of some g functions, and those g functions are, again, the binary functions, which have only one single 1 at the output, right? How many of those g functions do I need? Half of the number of rows in my truth table, right? So here in the truth table, I have 4 different rows, right? Half of them are 1. For every single of them, I want one of those g functions, right? So here I need 2 different of them. Now, if I have 2 to power d different cases, how many of those g functions do I need? I have 2 to power d different cases. Half of them are 1, half of them are 0, right? And for every single of those ones, I have one of those terms gi. How many of those terms gi do I have? 2 to power d divided by 2, half of the cases, right? 2 to power d divided by 2, which is 2 to power d minus 1, right? So this is the conclusion that any function that I have, even if it is the worst case function, the most complicated one, I can at the very end of the day write it down in that form, that decomposition. And that decomposition at most is going to have 2 to power d minus 1 different terms. So I basically need 2 to power d minus 1 different neurons in the hidden layer. And then I sum them up at the output layer. I'm going to have my function realized, correct? So this is the final conclusion. So moral of the story, if you want to just show your binary function with one shallow, it means just single hidden layer. If you want to show your binary function with that one, you need to have a hidden layer which is 2 to power d minus 1. And again, by shallow, I simply mean one single hidden layer. Everybody's clear? Any questions? Okay, now, do you think this is a kind of feasible thing I can do? Like, if we are talking about real practical functions, how many inputs do we have? Huge, right? D could be very, very large, right? I mean, probably you don't think of binary functions right now. We're going to get there. But right now, just think about binary functions. If I have a very huge dimensional binary function, then how many neurons do I need in my hidden layer? 2 to power that huge number, which is a super huge number, right? So this is the point where many people initially said that, okay, this idea of neural network sounds nice, is realizing representing any binary function. And as we're going to see shortly, once you can realize any binary function, essentially you can do whatever you want. But the point is that complexity is huge, exponentially large, right? If you have d-dimensional input, then you essentially have exponentially large number of neurons needed to just represent your function, right? But there is one simple observation that could help us understand that what we did here is actually unnecessary. So that is what I call it. So this is somehow made up term, nested decomposition. So I made it up. If I can represent my binary function in a nested form. And what do I mean by nested form? So I have binary function of d different values, right? So say d equals by 4. Let's think about the case where d equals by 4. So when I have d equals by 4, then I have 4 different inputs, right? So say I have 4 different inputs, x1 and x2, then x3 and x4, okay? Now, if I can group these two guys and compute a binary function out of them, g1. This is a binary function. So it's again 0 or 1, right? 0 or 1. And again, I group these two guys together, and again, I compute g2. This is binary again, 0 or 1, right? And then I can write down my function f to be a function of this group. So g1, g2. So these two together are given to, another function, g0, g1 and g2 are given to some g0, another binary function, and this guy is f. Okay, f of x1, x2, x3, and x4. If I can do that, okay, then life could get much easier. So, did you get the idea of nested decomposition? So it means that I just group my inputs, d different inputs, into half. Then I compute binary function of the first half. I compute the binary function of the second half. Then I combine those binary outputs, and I compute the binary function that I want out of those two different binary variables. So some of you might immediately see that this is possible. But if you don't see it, just again think of the XOR case. XOR is always the most complicated binary function you can think of, and that is possible. Yeah? Just look at this XOR case, right? If I want to XOR 4 different binary variables, well, I can just compute the XOR of the first two. I can compute the XOR of the second two, right? And then I can XOR those XOR values, right? So my final function is a nested function of XORs, right? So XOR of 2 variables, then again, coming out of those XORs, 2 binary variables, I again XOR them, and then I get my final function, right? So essentially, you can show that in the binary space, this is really possible. You can have this nested decomposition. And since you can have this nested decomposition, then we can actually realize this nested form much simpler, okay? Now, say that I have done this for you, okay? So say I have 2, say, magic functions, g1 and g2, which compute 2 binary variables, and then out of those binary variables, the only thing you need to do is to compute another binary function. Now, if you want to compute that binary function, so if you want to realize that g0 of g1, g2 by a neural network, how many neurons do you need? Just give you a few seconds to think about this. So I have g0. g0 is a binary function. It's a function of g1 and g2, and I have given you g1 and g2, right? So now you don't know what is g0, so you want to realize it by a neural network. How you can make sure that you can do it? How many neurons do you need? 2 in the hidden layer, right? and then you add them up at the output, right? So you exactly need that architecture that we had for XOR, right? So if you had the architecture for XOR, 2 hidden layers added up, that is going to be the most complicated binary function of 2 variables that you could have, right? Correct? So I can realize with only 3 neurons, 2 hidden neurons, 1 output neuron, with this neural network, I can realize G0, right? From G1, G2, correct? Now, the question is, so I can really realize G0 from G1, G2 with only 3 different neurons, so 2 hidden neurons and 1 single output hidden neuron. But you might tell me, okay, but at the end of the day, you need G1 and G2. How you can realize that? Well, again, I can think that G1 has this nested decomposition. And again, I realize that G1 by that nested decomposition with 3 neurons, right? And I keep on backtracking till I get to the very input, okay? So that might be a bit hard in words, but maybe we can just have a visualization and we get it, right?
In the example, we choose x1, x2 as group for G1, but in reality, it could be x1 with x3.
Yeah, of course, definitely, definitely. I mean, you just partition them, right? I mean, you can even do different kind of partitioning, but just to get the simple idea. Yeah. So I wanted to realize function f. F, again, is a function of d different variables, binary variables, right? So I told you if I give you G1, G2, you can just have this neural network, and that neural network going to get from G1, G2 to f, right? Now, how can I find G1, G2? Well, I could think that there exists a bunch of other inputs, right? For G1, 2 different inputs. For G2, 2 different other inputs. And then each of them, I can realize it, again, with 3 neurons, right? Same architecture, correct? And I keep on going backwards till I get exactly to the all inputs, right? Everybody's clear? Meaning that if you think of XOR, so if you have XOR of lots of variables, okay, first 2, second 2, third 2, and so on. Then again, you group them into 2, the result. And again, you XOR them. And you keep on going till you are finished with XORing, right? Clear? Everybody got the idea? Yeah? Now, is it a neural network? Is this architecture a neural network? Yes, I mean, it's a network of neurons, right? Of course it's a neural network, right? And now, what are the layers? I mean, we have a bunch of hidden layers here, right? The first one, the second one, and so on till the last one, right? So it's not anymore a shallow neural network. It doesn't have a single hidden layer, but it's a neural network, right? Everybody's clear? Okay. Now, I don't want you to really compute it right now for me, but do you have any idea what is the depth of this neural network? And I don't want you to tell me the exact number. If you can do it, that's perfect. But how is it changing with D? No, the depth. If I have 4, right? What should I do? I should get from 4 to 2, then from 2 to 1, right? So 4 divided by 2 divided by 2, right? If I have 8, I should get from 8 to 4, 4 to 2, 2 to 1, right? If I have 16, 16, 8, 4, 2, 1. If I have D, then this depth would be proportional to? No, the depth. If you have 6, if you have 4, then you have depth, say for instance, I mean it's proportional to 4 to 2, 1, right? It's 2, right? If you have 8, then it's going to be 1. So from 8 to 4, 4 to 2, 2 to 1. This is going to be 3. If you have 16, then you get from 16 to 8, 8 to 4, 4 to 2, 2 to 1. So it's going to be 4, and so on. Now if you have D, then it's going to be log of D, right? Log of D. The depth is proportional to logarithm of D, right? And the number of neurons you have here you can simply start counting that, okay? And if you do that, okay, I didn't do the calculation here, but it's going to be a kind of geometric series. And then it's a very simple calculation. You're going to end up with the fact that this architecture I showed you is going to have 3 times d minus 1 different neurons, and its depth is logarithm of proportional to logarithm of d, 2 times logarithm of d. Okay? Everybody's clear? Questions? So if you got no question, do you see any gain we have got here? Do we have any gain as compared to the shallow network we had initially? What is the gain? How many neurons do we need now? 3 times d minus 1, right? How many neurons did we need when we have only one single hidden layer? 2 to power d minus 1, right? So there we needed exponentially large number of neurons. Now we need linearly large number of neurons. We can do this one. That one is possible, right? Okay, so this is the whole idea of the deep neural network. When you make it deep, then you need less neurons. And that less neurons, it doesn't simply mean some linear order. Exponentially less number of neurons. And this is why deep learning is a thing, you know? Because now you can, when the number of computations you need to do is simply linearly scaling with your input, you can do it with your computers, right? But exponentially large, you cannot, right? Everybody's clear? Questions? Yeah? So this is a huge reduction, and this is simply possible because we are going for a deep neural network. It means that we are not having just single hidden layer, we have multiple hidden layers. And this is the whole story of deep learning. So deep learning, it simply means that you use a neural network which is deep. It has more than one hidden layer, right? And the deeper you make it, the better you can estimate anything that you have. Questions? Yeah. It's 2 times log 2 of d. Because for every single combination that you do, you actually need 2 different layers, right? The first hidden layer and the output layer. So this is the reason. I mean, what I did here is not the optimal one. I mean, the order is the same. I mean, the optimal order for this complex case is linear, but essentially you can do it even more efficiently. I just wanted to showcase that, how deep learning works. Okay. If you got no question, then you might tell me, okay, you showed us that if we have a binary function of size of d inputs, then any functions we have, we can realize it by a neural network, right? Well, what does it have to do with classification or regression problems that we do in practice? Okay, basically any classification problem that you have, you can write it down as a sequence of binary arguments. So it's a Boolean argument. What do I mean by that? So for instance, consider this one. And I did again a terrible idea. So the font is like super small. So now, okay, let me just show you here first. Then, so what I want to do, I want to just solve one simple classification problem. And that classification problem that I have is that I get a 2-dimensional input. So I have x1, x2 in the 2-dimensional space. But that 2-dimensional input is not anymore binary. It's a real number, right? 2 real numbers. So it means that I am in the 2-dimensional space, right? Say this guy is x1, this guy is x2, right? And now, when I do a classification problem, what do I do essentially? Well, I want one region for x's to be classified with something, and another region being classified with something else, right? So that is a classification problem. Say my classification problem is very simple now. I have these 2 different lines, and I want anything between them to be classified as 0, and if anything at the outside being classified 1. Okay? This is a simple classification problem. Any other classification problem you have is of the same form, only the shape of that region is more complicated, right? Now, is it a linear classification, the one on the board? Can I do it with one line? No, because if I do it with one line, any line I put, I mean, at the end of the day, some part of it is going to be classified same as this one. I want to be between two lines. But I can write it down in form of a Boolean argument. What does it mean? It means that I can think first of the first line, this top line, right? And I would say anything below it is 0, anything above it is 1. Okay? I can now think of a second line, this guy, the lower line. Anything above it is 0, anything below it is 1. And now, if I want to refer to that particular region, I just need to have a binary function, right? A binary function, which when it sees 0, 0, it's going to give me 0. If it sees anything else, it's going to give me 1. And I do know how to realize that function by a neural network, right? It doesn't matter how complicated that binary function is. I can, at the end of the day, make one neural network which can realize that binary function, right? So if I give you any complicated region, for instance, not like this, but I have something like this. So if I have something of this form, so say, for instance, I have this region, and then I have this other region here. So anything inside these two regions is 0, anything out of it is 1. It doesn't matter. I mean, it's a one classifier, one classifier, one classifier, one classifier, right? All of them linear, and then I combine them by binary arguments. It's going to be this region, and then same thing to this one, and whatever comes out of them, again, I combine them Boolean, right? Correct? So any classification problem that you have, you can always write it down as a sequence of Boolean arguments. Okay? Any classification problem, right? And then, of course, every single, that Boolean argument, that huge Boolean argument is a binary function, and you definitely can find one neural network which is going to realize that binary function, right? So, moral of the story, any classifier that you want to design is going to be actually a sequence of, different linear classifiers being combined with Boolean arguments, and that Boolean argument is simply a binary function. So you essentially need to design your simple linear classifiers at the very input, and then you just combine them by realizing a binary function. Both of them you can do by using neurons, right? Neural network. And because of that, you can have any classifier realized by a neural network. For instance, in the example we had initially on the board, so I can have one classifier, the top classifier, that is the one which is doing the, the upper line. The second classifier, classifier 2, is the one which is realizing the second line. And then if I want to combine them, I basically need to just get those Boolean outputs and combine them using a binary function. And I can again do it by a neural network, right? At the end of the day, X's are connected to the very output by a bunch of neurons, so it's a neural network, right? Any classifier can be realized by a binary, neural network. Everybody's cool? Yeah? Now, one thing that you might ask me is that, well, it's not really the case because we might have some curvature, right? Not all the regions when we are doing classification is like straight, right? So it could be curvature. We want to classify within a circle. Well, we can approximate it, right? So we can just design a polygon, and then we increase the number of edges on this polygon, and it somehow approximates very well that curved area, right? So a more precise argument is that we can approximate any classifier as accurate as we want by a neural network, right? Right? And if we want to have a very high accuracy, we need more neurons, right? More neurons, we can combine more, make more lines, can combine more binary arguments, And because of that, we can have better approximation, right? So this is the idea of universal approximation theorem. And the version that you see it here is the one which I am giving only for classifier now. So what it says if you have any general classification task, you can always approximate the optimal classifier for that task using a neural network. Yeah? So there exists always one neural network which is going to do the classification either perfectly or with a very, very high accuracy for you. This is the first thing, right? And the only thing that you need if you want to specify the accuracy is the number of neurons that you need. And one key feature of this neural network is that when you make it deeper, then the number of neurons that you need is going to drop exponentially, right? And it's a huge help, right? So if you see the problem is very complex, you just make your neural network deeper and deeper, then exponentially you need less and less neurons, right? Everybody's clear? Any questions? No question? Moral of the story, you can pretty much realize any function, any classifier using your deep neural network. And this is essentially what we started with. I mean, we wanted to find the right embedding function, right? And then what it says that if you have a neural network, you pretty much can realize any function. So that neural network is the best embedding function you could have. You don't need to go and search for embedding function. Just use the neural network, right? That's it. Any questions? Everybody's cool? So, if you got no question, just one last thing about this universal approximation. This is what we did here was essentially for classification. And you might tell me, okay, classification is accepted, but what about regression, right? What if we don't want to have a classification problem at the end? We want to really find a real valued output function. Well, we can again approximate it very well using those binary functions. How we can do it? Well, say I want to approximate, I have this real valued function f. So f could be a very, very complex function. It's getting d-dimensional input. The output of this function is also a real value, right? So it's not anymore a classifier which gives me just one class 0, 1, right? It could be any real number, like the regression problem we had. Now, what can I do? The space of this function that I have, let me first draw it for one-dimensional case. Say I have this very complicated function, okay? And here is the input x. So now I'm thinking of one-dimensional function. And now I have f of x. So this f of x could be a function of this form, for instance, right? Can I do it? Can I approximate it by a neural network? Well, I am going to grid the space that I am dealing with, right? So I'm going to say, okay, this is the first grid, second grid, third grid, and so on, right? Now I look at just one grid. And for this grid, I am going to take the average value of the function, okay? Say the average value is here, okay? I'm going to take this one, okay? Now, again, this is the next grid. The average value is, for instance, here. So I'm going to take this one. This is the next grid. So the average value is here. And I am going to approximate this function with these grid values. Now, if I increase the number of grids, that grid is going to be as close as possible to that function, right? So I can approximate that function very well, right? Now, can I realize that grid using a neural network? Well, realizing that grid is essentially a classification problem, right? Anything inside the grid is 1. Anything outside the grid is 0. That is classification. I can do classification by a neural network. So I can realize that grid. How many grids do I need? I just write one neural network for every single of them. I combine them. This is again a neural network, and it's going to approximate my function. So the whole idea is that you're going to make m different small grids, and in every single grid, you take the average value of the function. Okay? And once you have the average value of the function, you just make simple classifier. That classifier is going to give you 1 when you are within grid. If you're outside the grid, it's going to give you 0, right? And then you can approximate your function f with f hat, and that f hat is simply those average values multiplied by the corresponding classifiers, right? So thinking of a two-dimensional surface, it means that I make tiny square grids, and in every grid, my function is constant. But if I increase the number of those grids, then this approximation is going to get very, very close to the true function, right? So this is going to just conclude the general form of the universal approximation theorem. That says that if you have any function of a d-dimensional input, then you can approximate it by a deep neural network, or a neural network in general. Yeah? And how much accurate you want it to be. So how much you want the difference between your function f and your approximation f hat b, this amount of difference that you want, even if you think of the maximum difference you could get over inputs, like the worst case scenario, you can make it as small as you want if you have enough neurons, right? And this is this, great power, expressive power of the neural network. So essentially, you can make any function that you want if you have a neural network. And don't forget, if you want to make your accuracy more, you need more neurons, but you can always go in depth, right? Because when you go in depth, then the number of neurons you need is going to drop exponentially. And this is a very powerful thing. So with a finite number of neurons, you can do a very, very accurate approximation. Any question? Sorry? This is the supremum, like the maximum value you can think of, right? So you have your function, and your function could be like, here is very accurate. This is exactly the same. But here it has a huge difference, right? Not huge, but big difference, right? So I just go over x and look at the largest difference that I have. So it's the worst case error you could have. Yeah? Questions? No question? Okay, so now what I showed you here was that if you have a very complicated function, you can always make one neural network, and that neural network can approximate that function very accurately. So if you have a classification problem, you can learn that classification task properly by a neural network. If you have a regression, again, you can find that regression function accurately by a neural network. But the point here is that if you want to really get the true realization, you need to do training, right? So what I said here is that your neural network is capable of doing that. But at the end of the day, you need to find all of those weights and biases inside your neural network, right? So that is the idea of training, right? And these stories that I told you here, they were known for quite a long time. But nobody was brave enough to touch it. Because nobody thought that it's going to end up like we are going to find the right weights and biases, okay? So a tiny bit of history here is that there had been this story that I told you, this universal approximation. This was, the term universal approximation was around 90s or 80-something, okay? They came out. So one of the very famous people worked on it. One of the most referred papers in that respect was written by someone who was graduated from mathematics department here at UofT, okay? And even if you go older to that, just go and check Hilbert's number 13 problem introduced in 1900, beginning of the the last year of 19th century. He came up with 23 problems, and his 13th problem is basically this one, okay? So this is an old problem. Many people worked on it, right? But the key point here was that people, once they saw this universal approximation idea, they had the feeling that, okay, these units, these neurons, the computational units, They are very capable of doing what we want, but how we can make them do that. So how we can find those weights and biases inside this architecture to work like that. So we need to train them, and then many people thought, okay, I mean, if you want to train them, then you need to just go ahead and compute probably the empirical risk, and then you try to minimize that empirical risk. But now that empirical risk is going to be a super messy empirical risk, right? So how you can minimize it, forget about it. This is just a fancy idea, right? But then a bunch of people here at UofT insisted on that. So people tried to do this. LeCun tried to do that. Everybody came up with the idea that, okay, just use gradient descent. And if you want to compute the gradients, just use chain rule, which ends up with the algorithm backpropagation. But you can use it to just train a deep neural network. And if you cannot guarantee that you are hitting the right small loss that you want, okay, just make it deeper and deeper. But many people believe that these small group of people thinking about gradient descent and backpropagation, they are basically saying nonsense, right? So they're just dreaming. It's not going to work. And at some point in 2012, AlexNet won the ImageNet challenge, which was the first neural network beating non-neural network classifiers, right? And this was the point where people started to believe that, no, backpropagation, gradient descent, if you do it right, it's going to work. And this is where we ended now, right? Deep learning is pretty much used everywhere, right? So the next thing that we are going to do in the next lecture, we're going to just discuss this training. We just understand what does backpropagation mean and how we can use it when we want to do the training. Okay? Questions? No question? Okay, great. So you can take a look. I think Goodfellow textbook might be a better idea for this chapter if you want to learn more. But most of things are included. Okay? Nice. Have a nice one, and see you next week, right?